Welcome to today's lecture on particulate matter, aerosols, and atmospheric dispersion. In the previous lecture, environmental pollution and the physics of air pollution were introduced in general terms. Today, the discussion moves deeper into suspended particles and aerosols, which are among the most important atmospheric pollutants. These particles influence human health, visibility, weather systems, and Earth's climate. Very tiny particles can remain suspended in air for long durations and may travel over large distances before deposition. Particulate matter and aerosols are extremely important atmospheric pollutants because they directly affect human health, reduce visibility, modify weather processes, and influence Earth's climate system. Atmospheric dispersion explains how these suspended particles move, spread, dilute, settle, or accumulate under different environmental conditions. The image on this slide shows a polluted urban environment with visible haze and suspended particles. The reduced visibility demonstrates scattering of sunlight by aerosols. The industrial smoke plume indicates continuous emission of pollutants into the atmosphere. In this lecture, the meaning and classification of particulate matter and aerosols will be discussed first. Then the role of particle size in suspension, settling, and atmospheric transport will be explained. Particle size is extremely important because it determines whether a particle quickly falls to the ground or remains suspended in the atmosphere for long durations. The lecture also covers the forces acting on particles, their settling behavior, and atmospheric dispersion in terms of advection, diffusion, and turbulence. Finally, the environmental and climatic effects of aerosols, including their influence on visibility, cloud formation, and climate, will be explained. The book shown here, Environmental Physics by Boker and Van Grondel, is one of the major references for this course. Particulate matter, commonly abbreviated as PM, refers to tiny solid particles or liquid droplets suspended in the atmosphere. These particles may originate naturally or through human activities. Natural examples include volcanic ash, sea salt, and pollen, while anthropogenic sources include smoke, soot, and industrial emissions. The key physical idea is that these particles remain suspended because their size is small enough for air resistance and atmospheric motion to counteract gravity. The figure shown on the slide presents different types of particulate matter in the atmosphere. It includes dust, smoke, soot, liquid droplets, sea salt aerosols, and industrial aerosols. The figure also compares their approximate sizes and sources. Atmospheric particles vary greatly in size and composition, and these differences strongly influence their behavior. Particulate matter is classified according to particle size. PM₁ refers to particles with diameter less than 10 micrometers. These particles can enter the upper respiratory system. PM₂.₅ refers to fine particles with diameter less than 2.5 micrometers. These are more dangerous because they penetrate deeply into the lungs. Ultrafine particles are even smaller and may enter the bloodstream. The figure compares particle sizes with human hair and also illustrates how deeply different particles penetrate into the respiratory system. The important physical concept here is that smaller particles remain suspended longer because gravitational settling becomes weaker relative to air resistance and random molecular motion. As particle size decreases, suspension time increases and health risk becomes more severe. The motion of atmospheric particles depends on the balance between gravity and drag force. Large particles experience strong gravitational settling and quickly fall toward the surface. Small particles experience stronger air resistance relative to their weight, allowing them to remain suspended for long durations. Very small particles are also affected by Brownian motion due to collisions with surrounding air molecules. The figure on the right compares large and small particle motion. Large particles follow relatively direct downward paths because gravity dominates. Small particles move irregularly and remain suspended longer because drag force and random molecular motion dominate. This is why fine aerosols can travel long distances across cities, countries, or even continents. A suspended particle in air experiences several forces that determine its motion. The first force is gravitational force, which pulls the particle downward. It is given by F equals mg, where m is particle mass and g is gravitational acceleration. The second force is buoyant force, acting upward because the particle displaces air. The third force is drag force, which opposes motion through air. For small spherical particles, Stokes' law gives a drag force as 6 pi eta RV. Here eta represents air viscosity, r is particle radius, and v is velocity. The net motion of the particle depends on the balance among these forces. This directly connects aerosol physics with mechanics and fluid dynamics. When a particle falls through air, gravity initially accelerates it downward. As velocity increases, drag force also increases. Eventually, drag force and buoyancy balance the gravitational force, producing constant velocity called terminal or settling velocity. The force balance equation shown is Fg minus Fb equals Fd. Substituting all forces and simplifying gives the settling velocity equation. The final result shows that settling velocity is proportional to the square of particle radius. Even a small increase in particle size, therefore, causes a large increase in settling speed. The figure on the right shows particles of different sizes settling in the atmosphere. Large particles quickly fall toward the surface, while very small particles remain suspended for long durations. Very small particles experience continuous random motion due to collisions with surrounding air molecules. This irregular zigzag motion is called Brownian motion. The figure illustrates this process clearly. The central particle is continuously bombarded from different directions by rapidly moving air molecules, producing random motion. Brownian motion becomes very important for ultrafine particles and nanoparticles. Physically, this motion enhances dispersion and reduces settling because particles no longer follow smooth downward paths. Aerosols are suspensions of fine solid particles or liquid droplets in a gas, usually air. The atmosphere naturally contains aerosols from oceans, deserts, forests, and volcanoes. Human activities greatly increase aerosol concentration, especially in urban and industrial regions. Examples include fog, mist, smoke, sea spray, sulfate aerosols, and nitrate aerosols. Aerosols are not always harmful. Some are naturally present and play important roles in cloud formation and atmosphere processes. This slide compares natural and anthropogenic aerosol sources. Natural aerosols include sea spray from oceans, dust from deserts, volcanic ash, and smoke from forest fires. Anthropogenic aerosols include vehicle emissions, industrial smoke, biomass burning, and aerosols formed through atmospheric chemistry. The figure clearly separates natural and human-made aerosols. On the left side are natural sources such as volcanoes and oceans. On the right side, industrial activities and urban pollution represent anthropogenic aerosols. Human activity has dramatically increased atmospheric aerosol concentration. Primary aerosols are emitted directly into the atmosphere, such as dust and smoke. Secondary aerosols form inside the atmosphere through chemical reactions of gases. For example, sulfur dioxide can transform into sulfate aerosols, while nitrogen oxides form nitrate aerosols. The figure explains the full sequence from emission to atmospheric transformation and finally secondary aerosol formation. The atmosphere therefore acts not only as a transport medium, but also as an active chemical environment. Aerosols strongly influence visibility and climate. Aerosols scatter and absorb sunlight. Scattering reduces visibility and creates haze. Absorbing aerosols, such as black carbon, can heat the atmosphere. The figure explains aerosol-climate interactions. Some aerosols reflect sunlight back to space, producing cooling, while others absorb radiation, producing warming. Aerosols also affect cloud formation and rainfall. The direct effect refers to scattering or absorption of sunlight itself. The indirect effect refers to aerosols acting as cloud condensation nuclei and modifying cloud properties. This figure combines two important atmospheric processes. On the left side, pollutants and aerosols disperse in the atmosphere after being emitted from a source. Wind transports them, while diffusion and turbulence spread them outward. On the right side, aerosol particles act as cloud condensation nuclei. Water vapor condenses onto these particles, forming tiny droplets that eventually grow into clouds. This connects aerosol physics directly with cloud physics and climate science. Advection is transport by bulk air motion. The equation F equals UC represents pollutant flux due to advection, where U is wind speed and C is concentration. Stronger winds transport pollutants more rapidly and over larger distances. The figure demonstrates several connected processes, including aerosol formation, climate interactions, cloud droplet formation, and large-scale plume transport by wind. The lower image particularly shows how a pollutant plume stretches horizontally due to wind transport. Diffusion spreads pollutants from regions of higher concentration toward lower concentration. Fick's law describes this process mathematically. The negative sign indicates movement toward decreasing concentration. In the real atmosphere, turbulent diffusion is usually much stronger than molecular diffusion. Turbulent eddies mix pollutants rapidly in all directions, producing much faster dilution. The figure shows a pollutant cloud becoming progressively wider and less concentrated as it moves downwind. This slide introduces one of the most important models in atmospheric pollution physics, the Gaussian plume model. It predicts pollutant concentration from a point source, such as a chimney. The equation contains the emission rate, wind speed, stack height, and dispersion parameters. The Gaussian shape arises because turbulence spreads pollutants approximately symmetrically around the plume center. The figure clearly shows highest concentration near the plume center line and decreasing concentration away from it. This model is widely used in environmental engineering and air quality prediction. A temperature inversion suppresses vertical mixing and traps pollutants near the surface. Fine particles enter deeply into lungs, and ultrafine particles may even enter the bloodstream. Aerosols reduce visibility, affect ecosystems, modify rainfall patterns, and damage buildings. Aerosol physics, therefore, directly affects public health, climate, agriculture, and infrastructure. Particulate matter and aerosols are important atmospheric pollutants. Particle size controls suspension and settling behavior. Aerosols affect visibility, climate, and cloud formation. Atmospheric dispersion controls pollutant transport and dilution. Understanding these processes helps prediction, monitoring, and pollution control. These assignment questions focus on the most important concepts discussed in the lecture. The first question explains why PM₂.₅ is more dangerous than PM₁. The second question derives the settling velocity relation using force balance. The third question explains Brownian motion physically. The fourth question discusses the Gaussian plume model conceptually and mathematically. The final question explains aerosol effects on climate. Thank you very much.